始只看到了志愿者阵容。
Hello, everyone. I'm Yulo from the Tsinghua University. Today, I will present our work, Synthesizing Natural Language to Visualization, NL to VIS benchmarks from NL to SQL benchmarks. Let's begin with the motivation. We can look back at the evolution of the visualization interface. Suppose we have a dataset about the COVID-19 dataset from the United States. And suppose the user want to create a bar chart showing the top 5 states with most confirmed cases. A long time ago, the user may need to write computer graphics code to visualize data. And thanks to the declarative visualization language, the user can use the D3 or Visualize, only use a few lines of code to visualize data. Or the user can choose the GUI-based visualization tools such as Tableau and Power BI, or use the recommendation tools such as the DeepI and CDB. In terms of the easy to use, the natural language interface for creating the visualization is the simplest way for the user. Recently, both commercial vendors and academics are starting to explore the NL to VIS systems. For example, the NL for DV from VIS 2020 and the Tableau Power BI. However, most of these systems are mainly based on the semantic parsers or handcrafted rules, and only support simple or constrained NL queries. Given this context, we made the first observation. That is, the deep learning-based techniques should be used to improve the performance of the NL2V systems, just like the sequence-to-sequence based models for translation. However, the big obstacle for these proposals is lack of the benchmarks. So, our goal in this work is to fill this gap. What is the NL2V benchmarks? The NL2V benchmark consists of a large number of natural language and visualization pairs over the datasets. And we use the NL2V benchmarks to learn, develop, and evaluate the NL2V systems. Note that the visualization can be represented as the Vegalite or other declarative language format. So, the goals in this work is to developing the NL2V benchmarks such that have large number of NL-V pairs and have good quality and good coverage. The traditional method for developing the benchmarks usually has two steps. The first step is manually design and collecting comprehensive set of data and queries, and then ask the expert to complete the task. The first limitation for the traditional method is high human cost. And the second limitation is not extensible. It means for any new dataset, one has to repeat above two steps from scratch. Given this context, we made two observations. The first observation is the SQL query and visualization queries have we can learn the translation from the MV bench. And we compare with our solution to other solutions in the NL2V task. The first is the DeepI. DeepI is a rule-based methodology for creating visualizations. And the second is NL4DB from VIS 2020. The NL4DB is a toolkit for NL2V task based on the NLP semantic parsers. The table reports our results. We can see that the learning-based method significantly outperforms the rule-based and semantic parser-based approach for the NL2V task. So, in summary, we propose the first NL2 sequence to NL2V synthesizer that can synthesize multiple NL and V pairs from one NL and SQL pair. And we produce the first NL2V benchmarks, NV bench. We're also the first to apply a neural translation model on learning the NL2V task. And we open source our code and dataset in the below link. Thank you for your listening, and questions are welcome.
See your question?
Can you hear me? 没有是吧？
我们都没有开音。
Yes, yes.
都没有。OK.
You want to tell you?
Yeah, are you there? Can I
I'm here.
Attention?
I'm Yu.
Good. So will you open source your dataset and benchmark?
Yes, we have released our dataset on the Google site, and you can download the dataset and the code via the below link.
Okay, good. Thank you.
Thank you, Professor.
Hello, Yu.
Hello.
A good job.
You did that go.
Thanks for this encouraging comment.
Thanks for sharing.
Hello, dear Yu.
Hello, I'm here.
I want to ask how many pairs in the database? Dataset.
Okay. We have more than 150 database, and we collect 780 tables. Based on this, we have the MV bench consists of the 20,000 NL and VIS pairs.
Okay. I know. Thank you for your answer.
Thanks.
Thanks for watching up. Because of the limited time, we gave a chance to Xinyang.
Hi, you can hear me?
Yes.
Yeah, I remember a slide you shows lots of logo like the industry, like the products in industry and in academics. Could you illustrate small information about this slide?
Okay. You want to
是你在帮忙拖吗？
对，所以说志愿者就要帮忙拖了。
为什么不能让他再去共享一个 PPT？ 有人让他搞。
对，之前不就说不会给那个。
他不需要他在家庭权限，他就能共享一个。
那这种情
况要结束，就是说看怎么办吧，这种情况。
那这个关了之后，现在显示的应该是那个吧？现在那个，
你现在切换，然后你切换第二个视频，你说，你就说是，因为它是3个人的号。
我现在马上切换第二个视频。
不是，现在等3人开始说话呀。
Okay. Due to the limited time, thanks for.
就是之前 ICDE 的时候，就是 QA 环节的时候，他是把那个权限全部给那个。
Hello everyone, I'm Sun Ji from Tsinghua University, and I will introduce our paper, The Learned Cardinality Estimation for Similarity Queries. Cardinality for similarity search denotes the number of objects in dataset whose distances to a query queue are not greater than a distance threshold tau. And cardinality for similarity join denotes the total number of pairs QP from query set and dataset whose distance is not greater than tau. There are some methods being proposed for similarity queries. The kernel density estimator also has zero-tuple problem because it relies on sampling. The linear mixture model is less powerful to feed high-dimensional data. The variational autoencoder-based method cannot produce distance-aware representations, and it needs a lot of training data. The basic idea for solving cardinality estimation problem for similarity queries is using a modularized neural network. In this neural network, key features like query vector, distance threshold, and data sample are input into different layers and transformed to a single representation. And we use another learned neural network to predict the cardinality. All the layers in the neural network is learned from existing training queries and their true cardinalities. Hello everyone, I'm Sunji from Tsinghua University, and I will introduce our paper, The Learned Cardinality Estimation for Similarity Queries. Cardinality for similarity search denotes the number of objects in dataset whose distances to a query queue are not greater than a distance threshold tau. And cardinality for similarity join denotes the total number of pairs QP from query set and dataset whose distance is not greater than tau. There are some methods being proposed for similarity queries. The kernel density estimator also has zero-topple problem because it relies on